All right, new set of hybridization in this video. We've looked at sp3, we've looked at sp3d, and sp3d2. Looked at hybridization schemes and how they match Lewis structures. I saved these ones for last because I think these are a little more complicated. We have to introduce some new terminology for you. For sp and sp2 hybridization, this is what you're going to see when you have a Lewis structure with multiple bonds. Right? So again, when you do the 6m plus 2 minus number of valence electrons, you get a positive value, which could be an electron deficient structure, or multiple bonds, or a ring, but in this case, we're going to look at multiple bonds. So i.e. double or triple bonds. So you got the single bond plus an extra line for the double bond, or an extra 2 lines for the triple bond. Right? That first line is kind of your single, and then the extra line is a multiple bond. Well, the terminology we're going to be using to explain this is different than we do in introductory or high school chemistry typically. Sigma bonds, which I've mentioned before, are due to head-on overlap of orbitals, usually hybrid orbitals, right? Head-on collision, meep, meep, oh man. So this is atom A and this is atom B. This is a hybrid orbital, that's a hybrid orbital. They overlap directly like two cars with a head-on collision. Boom! So there's an electron density in between them along the internuclear axis. That's called a sigma bond with that notation there, which corresponds to a single bond. So all single bonds are sigma bonds. But not all sigma bonds correspond to single bonds. We're going to find out when you have a double bond. The first line is a sigma bond. The second is a special kind of bond called a pi bond. And a triple bond, the first line is a sigma bond, and the extra 2 lines are pi bonds. So we need to incorporate this pi bond concept for multiple bonds. But the first one's always a sigma bond. All right, a pi bond is due to side-by-side overlap, not head-on. Side-by-side overlap, but not of hybrid orbitals, of unhybridized p orbitals on adjacent atoms. I'm going to have to draw this on the next board. So if I end up with an unhybridized p orbital, say in the z-axis on an atom here, and an unhybridized p orbital on the z-axis on an atom here, and they're right next to each other, those p orbitals overlap in the positive and negative lobes, so you get electron density above and below the internuclear axis. This is a harder concept. Let's draw that on the next board. Okay, you ready? Pi bonds wig people out the first time they see them. All right? Sigma bonds are pretty easy. Boop! Kind of like valence bond method, and the head-on overlap, that's all we really think about. But what if you have unhybridized p orbitals, like with sp and sp2, right? If I do sp hybridization, I only need one s and one p. I'm not using the other two, so maybe I use the px. What about the py and pz? You're not using them. They remain unhybridized. We're going to see that when we do the hybridization scheme. For sp2, s, say px and py. Well, the pz we didn't use, so that's left unhybridized. Potential for the multiple bonds. Pi bonds, you ready? Pi bonds again. So let's say I have atom A and atom B. Whatever its hybridization is, let's say we have an extra leftover unhybridized p orbital, let's say in the pz direction. So atom A has an unhybridized orbital with a positive negative lobe, different colors. And the atom next to it, B, and there'll be some electron density here we'll look at with a sigma bond, not important right now. We're focusing on the pi bond. So let's say the atom B right next to it, adjacent to it, also has an unhybridized pz orbital. They have to be in the same axis. You can't have a pz and a px, right? They have to be parallel to each other. Do you see that side-by-side overlap right there? Oh, it's like a collision with two cars, but you're traveling on the freeway together and you kind of bump. That happened to me once, right? The dude next, well, maybe it was me. Probably. I was talking to my friend and I kind of weaved over to the other lane. Bonk! And I bumped into the car next to me and they're like, oh, my neck. And I'm like, oh my God, gotta be kidding me. I just barely tinked. I didn't even notice. So versus a head-on collision, big difference. Versus tink, right? So horrible analogies, but I'm the master of bad analogies. So do you see the red there? The electron density is a little bit below and a little bit above the internuclear axis. That's much different than a sigma bond. Sigma bond, the electron density is in between the nuclei. So a sigma bond would be right here. So we're going to see a double bond later. It's like a hot dog with a bun, right? The hot dog is the sigma bond. The bun, which is above and below the hot dog, is the pi bond. Oh, kind of weird, huh? So that's due to unhybridized p orbitals side by side or adjacent overlap. That's a pi bond. That corresponds to any extra line in double and triple bonds. The first line will be a sigma bond due to head-on collision overlap with the electron density between the two atoms. And then the second line for a double bond or the second and third line for a triple bond will be due to unhybridized p orbitals overlapping side by side. Those are your multiple bonds. So remember that, multiple bonds require pi bonds. Ooh, so this will make more sense when we do the orbital overlap diagram where you can actually see these happening. So let's do some hybridization schemes and show you how this predicts this these pi bonds. Ooh, it's gonna get crazy. Here we go. Let's do sp2. I think it's a little easier, and then we'll do sp. So sp2, let's take for an example H2CO. Pretty simple organic molecule. Do our 6n plus 2, which is 14. Valence electrons is 12. 14 minus 12 is positive 2. So couldn't be a carbon ring. We only got one carbon. There's no boron, beryllium, or aluminum, so it's not an electron deficient species. So that must be one multiple bond. Right there. Can't go to the hydrogen, right? So here's the Lewis structure. Now let's take a look. We've got a single bond, double bond. That's 3 electron groups. 3 electron groups is the same as 3 hybrid orbitals, right? So from Lewis and Vesper theory, the number of electron groups equals in valence bond theory, hybridization, the number of hybrid orbitals. So that'd be 3 hybrid orbitals. To get 3 hybrid orbitals, I need to hybridize 3 atomic orbitals, which would be s always, then one of the p's, another one of the p's, and that's it. S plus P is sp2. That leaves an unhybridized p orbital, right? So that leaves 1, and whichever one it is, doesn't matter. You can say pz and then rotate it, and now it's a px, right? Unhybridized p orbital. Whether that's px, py, or pz, you just pick it when you're doing your diagrams later. You just pick the one that makes the diagram look the best, right? Whether it's pz, px, or py coming at your face, right? I always think the camera's up here, but I always think it's over here. I'm looking at this red square, so I look at that a lot, but the camera's actually right there. Hi, Mom. All right, let's draw what that looks like real quick. All right, we did this for sp3, not for sp3d and sp3d2, where we took the 3 atomic orbitals and then hybridized them to get the number. Well, however many atomic orbitals you take, that's the number of hybrid orbitals you get. So in this case, for sp2, right, we got 3 electron groups. Let's take the s. Let's take the px and the py. We could have taken pz and py. Doesn't matter. 3 atomic orbitals gives us 3 equivalent degenerate same energy hybrid orbitals due to constructive interference and destructive interference. So the red part of the p orbitals, so the orbitals get a little more bulbous. So the p orbitals, they become a little more bulbous because of the spherical S shape. And you get this little destructive interference, little dangly thing. And when we overlap them all, those 3 just overlap in the middle and we don't draw them. All right? And then I'm not going to worry about the positive, negative lobes for you guys. And then we have one in the x direction here, one coming kind of out this direction and one coming away from you. So this is actually, it's in the same plane. They're all in the x-axis here. But you've got one coming kind of towards me this way, away from me here. Kind of hard to draw in 2 dimensions. But it's a trigonal planar structure. So those 3 hybrid orbitals, it's like those frisbees. It's not a boomerang. It's like a boomerang with 3 things, right? So it comes off and you can throw it. I don't know if you've ever seen those. It's kind of weird. So it's like a 3-pronged boomerang. That's kind of what it looks like. And it's flat. It's planar. And you've got the 120-degree bond angles. But we do have an unhybridized pz orbital, which we can draw. Let's do that on the next board. Let's draw these 3 hybrid orbitals now that sucked up the s, the px, and the py. We don't need any d orbitals for this. Let's draw that unhybridized pz orbital and show you what that looks like as a potential for a multiple bond. Hey, hey. And that's the match with the Vesper. Right? I don't think I did that for the sp3d2 on the last one. You get this octahedral arrangement of those 6 sp3d2 hybrid orbitals. That's pretty straightforward. Told you this is a little more complicated. All right, so we've got those 3, right, sp2, right, sp and p. We've got those 3 sp2 hybrid orbitals in a trigonal planar structure. It's flat, it's planar, 120-degree bond angles. Those can overlap head-on only. Hybrid orbitals can only be head-on overlap, so those can form sigma bonds. Right? So those will form single bonds or the first line of a double or triple bond. But this unhybridized pz orbital, positive, negative love, can overlap if there's another atom next to this, bonded to it, that also has an unhybridized pz orbital. They can overlap side by side to give electron density above and below the internuclear axis. Well, those can form pi bonds. Hey, doesn't mean it's going to, but if you have an unhybridized p orbital, that has the potential to form a pi bond if it happens to connect adjacent with another atom that also has an unhybridized p orbital in the same axis. If it's in the py and pz can't overlap. Pz and px can't overlap. It has to be px, like this, py, or pz. They have to be in the same axes to do it. Woo! Let's do a hybridization scheme for that and see if it matches our CH2O. It's going to get a little weird, guys. Hybridization scheme for the carbon atom, central atom. We can do it for the oxygen as well, but let's focus on the carbon atom. Let's look at the carbon atom on the periodic table. Remember, we do the unhybridized carbon atom, or whatever atom it is on the left. Carbon happens to be right there. That's in N equals 2. And there's 1, 2, 3, 4 valence electrons. There's no charge on this. So we've got the 2s and the 2p. We don't need any d's, right? We've got 4 electrons. Is that correct? So 1, 2, 3, and 4. And you can put those anywhere. Doesn't matter. These are all degenerate. And I don't designate px, py, pz in this scenario. But imagine this is px, py, pz. Have fun with it. This is sp2 hybridized. We determined before because of the 3 electron groups, right? 1, 2, 3 electron groups, 3 hybrid orbitals, spp. So we need to do a hybridization scheme that predicts 2 sigma bonds here, a sigma bond and a pi bond, or 2 single bonds and a double bond. Let's do that. But remember, a double bond now we're thinking as a sigma plus a pi. A single bond is a sigma bond. I should probably reiterate that. So I need the s orbital and 2 p orbitals. These aren't the same anymore, right? So I need the s. Which of the 2? I need 2 of those 3 p orbitals. If you pick the wrong 2, you're not going to get the right structure. You've got 2 of them with an electron in it and 1 that's empty. So we can either take the 2 with the electrons or the empty one. So the rule is always take the empty one first. Right? So that remains unhybridized in that scenario. So I should make a note of this here. Always hybridize empty p orbitals first. So hybridize empty p orbitals first. Keep that in mind. Otherwise, it won't match. So if you're having a lot of, if your hybridization scheme is not predicting that, it's because you're probably hybridizing the one that's half filled before the empty one. Take the empty one first, and this should work out. So I circled 1, 2, 3 boxes, right? 3 boxes. So let's draw our 3 boxes. And these are our sp2 hybrid orbitals. How many electrons did we circle? 1, 2, 3. See that? So let's put our 3 electrons in there. They're not paired up. See, if we took this one, we would end up predicting a lone pair. That ain't right. So that predicts 3 sigma bonds. But remember, we have this unhybridized p orbital. What? So that comes around here. That's the oh, like I'm coloring myself. Ooh! So we've got the 1 p orbital here with a single electron in it. We have not run into that, my friends. That predicts a pi bond. Hey, that is the extra line right there. So this predicts three sigma bonds. 1, 2, 3 sigma bonds. So if you get a single electron in a hybrid orbital, that predicts a sigma bond. So that would be here, here. I'll do those in blue, right? So sigma bond, head-on overlap between the orbitals between the carbons and the hydrogens, head-on overlap between the hybrid orbital of the carbon and the oxygen, boom, head-on collision. And then this predicts +1 pi bond. So that's the pi bond. Those are your sigma bonds. So let's do the pi bonds, say, in purple. There's your pi bond. So sigma, 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 pi. We're going to do something called a bonding scheme in the next video that shows exactly that. It draws either the Lewis or the Vesper structure and points to every line and tells you whether it's a sigma bond or a pi bond and what two orbitals are overlapping, either head-on for a single bond or side-by-side for a pi bond, to accomplish that. There you go. So that matches. Yay! And if you had circled this one first, you would have predicted no pi bond, 2 sigma bonds, and a lone pair. That wouldn't have matched. You'd be like, something's wrong, coach. What do I do? So we'll get to bonding schemes and orbital overlap diagrams in later videos. I want to do specific videos for those, so I'll bring these back up again. Let's do sp hybridization. Yeah! Actually, before we do the sp hybridization, I'm going to show you if we did the Molly-Mod set, what that carbon would look like, right? So we have 3 hybrid orbitals. That would be these little gray sticks there. Do you see the trigonal planar there? It's flat with 120-degree bond angles. That's the result of those 3 hybrid orbitals we get. And then we have this unhybridized p orbital. In this case, it's the z-axis. Oh, now it's the y-axis. Oh, now it's the x-axis. Just depends how you do it. But can you see that? Right? So we used up an S, a P, and a P for these. And then we have an unused p orbital here. So if that's a side-by-side overlap, we're going to get a pi bond. So that's what this is what you would do for the carbon atom in that scenario. And then we'd connect a hydrogen here, the oxygen here, and that's your sigma bond. And then that oxygen would also have unhybridized p orbitals. Ooh. We'll get to that in a little bit. All right, now let's do sp. Let's do sp. This is, to me, the most challenging one to conceptualize. So sp hybridization, classic example is C2H2. Is that acetylene? I think like an acetylene torch. Anyway, let's take a look. 6n plus 2 minus number of valence electrons gives you 14 minus 10 or plus 4. No boron, no beryllium, no aluminum, so it's not electron deficient. Not enough carbons to form a ring, so that must be 2 multiple bonds. Well, you can't have a multiple bond to a hydrogen, so it's got to be a triple bond. It has to be. There's your 2 electrons. So now remember, this is going to be a sigma plus pi. That's what triple bonds are. We'll summarize that later. So we got the carbons are the same, right? They're both central. We've got a single bond and a triple bond. So we got 2 electron groups on each carbon atom. So the hybridization is going to be the same on both of these. They'll be identical. That means 2 hybrid orbitals. That means 2 atomic orbitals we need to hybridize, S and P. So we're going to get sp hybridization, leaving 2 of our p orbitals unused. So maybe we hybridize the px, leaving the py and the pz unhybridized. Ooh, can you see where we're going to get the potential for 2 pi bonds? But they're going to be unhybridized p orbitals in 2 different axes, right? Maybe both in the z, both in the y, or 1z, 1y, or 1x and 1z. It doesn't really matter. Let's have a look at that real quick, and then we'll do a hybridization scheme. It gets a little wonky here. You ready? You ready? sp hybridization, right? Let's take the s, and you could take any of the 3 p's. Let's just take px because it's easy to see. Positive, negative lobe. Let's take those atomic orbitals, hybridize them to get the hybrid orbitals. Constructive and destructive interference, leaving you 2 hybrid orbitals, identical, pointing in opposite directions, right? And here's the little destructive interference, the little red things. They're going to meet in the middle. We'll just ignore those. And then the constructive interference, so you get what look like p orbitals that they're more bulbous. It's a cool word, bulbous. And so when we overlap those 2 hybrid orbitals, it looks like that, which looks like a linear structure, which is what 2 electron groups gives you, right? Remember in Vesper theory, Lewis theory and Vesper theory, 2 electron groups gives you a linear structure with 180-degree bond angles, right? So hybridization, so valence bond theory with hybridization predicts, well, gives you the same result. But remember, we've got the Py and the Pz unhybridized. So let's draw that on the next board. Let's draw the same thing with the two hybrid orbitals sticking out along the x-axis. Let's draw the unhybridized Pz, 2Pz, and the unhybridized 2Py. Oh, see if you can draw that before me. Go, go, go. This is what it really looks like. Okay, so you've got the sp and sp, right? You've got the two sp hybrid orbitals. But we have an unhybridized p orbital, say in the z-axis, and an unhybridized p orbital in the y-axis, coming at your face. So I'm going to kind of tilt it like this so you can kind of see it. So, right, how do you draw 3 dimensions like that on a 2-dimensional board? Kind of hard to do. So you've got this unhybridized, that happens to be a 2pz orbital, and an unhybridized 2py orbital. So those sp orbitals, these hybrid orbitals, can form head-on overlap or sigma bonds. The Pz, right, if this is the Pz, if that's next to another atom with also an unhybridized Pz orbital, that side-by-side overlap can form a pi bond. But so can the Py. So if the Py is actually tilted this way, if that's next to another atom, also with an unhybridized Py, it can form a second pi bond. You see how a triple bond is a sigma plus a pi in one axis plus a pi, peek boo, in the other axis. Oh, see that? Oh, my goodness. Let's do a hybridization scheme. See how that works out. See the 90-degree angles between the pi bonds here, 90-degree angle between the sigma pi bonds. Hey, hey. But 180-degree angle between the sigma bonds. I have a very bad habit of sticking my ugly mug in the way, so I don't know if I gave you, I just got to give you like 1 second where I'm like this, and you go pause. And then you can write the board. I bet people leave me, I'm like, move your head just a little bit like that. Okay, so we're good now? So now you can pause it and write that. All right, let's see if you can do the hybridization scheme on your own. So here's a hybridization scheme for our Lewis structure. There's our Lewis structure. So we need to predict the two sigma bonds here, a sigma, a pi, and a pi for the triple bond, correct? So let's draw that up here. All right, so this will be a pi. Let's call that pi 1, pi 2, sigma, sigma, sigma. We're going to see that that's called a bonding scheme later, right? So we should predict the sigma bonds here and the pi bonds there. But we're going to look at just one of the carbons, right? So let's just look at that carbon. So we should get a sigma here, pi there, pi there. Well, let's do it. Here's our carbon atom right there. Boop. All right. So that's an n equals 2. We've got 1, 2, 3, 4 valence electrons. No charge on the Lewis structure to worry about. So let's put in our 4 electrons. 1, and a 2, and a 3, and a 4. Or if you wanted, you could do it this way. Because they're degenerate. Let's just do it because we can. All right. So we need sp hybridization. And that is because, again, we have 1, 2 electron groups. Is that correct? So we need the s. We're only hybridizing one of the p orbitals. Which one should we take? Always take the empty one first, right? Don't take one of those. We're going to take that one. And then those 2 p orbitals that are unhybridized move over. All right, so we circled 2 boxes. We hybridized 2 boxes, so that'll give us 2 of those hybrid orbitals. So these are our sp hybrids. Getting used to hybridization schemes yet? How many electrons did we circle? 1, 2, correct? If you took one of those, you'd end up with a lone pair, which would, you'd end up with 2 electrons in there, which would predict a lone pair. There's no lone pairs in the acetylene up there. All right, we've got 2 unhybridized p orbitals. And that could be 2px, 2py, or 2py, 2pz, doesn't matter. And there's an electron in that one, same energy, and an electron in that one. But the hybrid is 1 part p. It's actually probably exactly in between because it's 1 part s, 1 part p. So it should be exactly in between the unhybridized p and s, or 2s and 2p. So what does this predict? Let's take a look here. Remember, unpaired electrons in a hybrid orbital predict 2 sigma bonds. You ready? You ready? Sigma bond. Sigma bond. That'll be true for each carbon. This carbon would be sigma bond, sigma bond. So it's the same. I said both carbon atoms. You don't have to do 2 separate hybridization schemes. They're exactly the same. Just say they're both like that. Got our energy scale here, increasing energy. Now this predicts, remember, if you have an unpaired electron in an unhybridized p orbital, that's a pi bond. Since we have 2 of them, that predicts 2. Let's do that. Let's do that in purple. I have a cat yowling somewhere. 2 pi bond. Pi bond. That would be this line here. Right? And that line there. So we could say this sigma bond goes from the carbon to the hydrogen. That sigma bond goes from the carbon to the other carbon. That pi bond is the second line, and that pi bond is the third line. Oh my goodness. Craziness. So that is a match, gang. That matches our Lewis structure. So we're going to bring all of this together. We've done SP, sp2, sp3, sp3d, and sp3d2. That's it. Those are the only possibilities. I've showed you the hybridization schemes, how we match the Lewis structure from the hybridization scheme. So we're going to look at bonding schemes. Lots of scheming. We're going to look at bonding schemes, which is similar to what I did there. And then we'll look at the culmination of all of it, orbital overlap diagrams, which are like the balloon animal structures. And we'll put this all together so you can look at bonding in a slightly different way. Ba-ba-boom!